Hey everybody, welcome back. We are going to be getting deeper into the functions and roles of network components. All right, routers, layer 2, layer 3 devices, firewalls, intrusion prevention systems, access points, controllers such as DNA Center and wireless LAN controllers. Okay, some things I'll get into detail about, others I'll just make mention of it, and you will have to dig deeper if you want to know a little bit more about that on your own. Okay, the thing that we need to first talk about before we get into the function of these devices is I really need to, I was going to start drawing, but let me talk about how LANs were years ago, you know, back in the 90s, the 1990s when I first got my exposure to networks. Computers were connected with a cable. You know, they were strung together and daisy chained with a single cable in the local area network. It was known as, it was a coaxial cable, much like the RG cable that connects to your cable TV. Okay, it was known as Thinnet. I'll show you a little bit about it here. 10^2 is one of the IEEE standards for Ethernet, and it was a 10 megabits per second. You can see a picture of a connector here. This was what connected into a T connector, so this cable connected in here, and this T connector connected into the network interface card on a computer. Okay, this was what the local area networks were made up of. They called it cheaper net or thin net. Okay, and then a thicker version of it was called thicknet, 10 megabit, 10^5, thicknet. It had this vampire tap. Literally, you would take this orange tool with a pinpoint on the end of it, and you would you would grab it with your hand, and you would go back and forth and core in to the sheath of this yellow cable, such that this vampire tap could then be tapped into the wire in the center there, and then it would adapt the signal across this vampire tap into this 15-pin DB15 connector known as an AUI, an attachment unit interface. That AUI connector would then use this was all a clunky system. It was heavy. It would hang off the back of your computer. And so this AUI cable would plug into an AUI connector on a network device, whether it's your NIC in your computer or a bridge or a router. Okay. So this is the beginnings of, this was some of the early technology of Ethernet. Okay. And so I mention all that to begin the conversation about domains within a network. All right, so let's look at that. Back in the day, you had computers, as I just described, and they all had this T connector on the thin net strung together like this. Okay, the T connector was right here, and the T connector would literally screw into the back of your computer. And then segments of the cable, this could be a 10-foot segment, this could be a 35-foot segment, doesn't really matter. But there was a limit to how far this thin net could go. We're not going to spend a whole lot of time on this, but I just want to describe it. There was a terminator here and a terminator here, and not all these computers could talk to each other. Okay? Something you need to know was the way that they would decide on how they would talk is a protocol known as carrier sense multiple access with collision detection. So the NIC would listen, then it, carrier sense, it would sense carrier, it would listen for an electrical signal, and which allowed for multiple access, and then it would detect collisions. Collisions aren't a bad thing. They were a normal occurrence in Ethernet networks of the day. So this was very much a half duplex type of a communication, where you can send, but this person can't send while you're sending. And so if two computers tried to send at the same time, they would sense the electrical signal on there, and there would be a subsequent jamming signal that would sit there, that would send a jam out on the wire, and all the computers would back off in a certain amount of time. Okay, and then they would try again. Excessive collisions are known as when the network interface keeps track of how many times it's tried to communicate. Those excessive collisions would be greater than 16, I believe. And so when you had excessive collisions, it might have been because you had too many devices on the network. So you had to separate these with a bridge. Okay, a connector would go in here, a connector would go out here, and you would have a different LAN segment. Then when you had a bridge here, excuse me, this bridge was a layer 2 device. Well, then what was all this? This is a layer 1 domain. It was an electrical domain. As I described, there were electrical activities going on that we were keeping track of, jamming, carrier sensing. And so this collision, this collision environment was known as a collision domain. The word domain is you can use it in a lot of different terms. I mean, a person or animal's domain is the area of control or visibility. A lion's domain would maybe be the domain for which African lions, it's like their territory, okay? And so just kind of describing in a loose term the idea of domain, but very specifically the extent to which a collision can reach would be known as the collision domain. Okay, so this would be the collision domain from the terminator of this cable on the end to where the terminator was previously, or where we've disconnected the terminator and now connected it into a layer 2 device. Okay? So we had the collision domain. Now, when we take this a step further, we had multiple computers. Let me just draw these as circles. Or let me position myself a little bit better so I can draw faster. When we had multiple computers with T-connectors and Thinnet, and we had the the bridge in here. The reason I'm calling it a bridge is because that's what they were called early on. Then we had another collision domain over here. Of course, the bridge separated the two collision domains. So here's collision domain number 2. Here's collision domain number 1. But the bridging domain extends from here to here. So these computers could bridge to one another through the bridge, through this layer 2 device. They could all talk to each other through the bridge. So the domain to which the bridge would allow traffic to flow is known as a bridge domain, otherwise known as a broadcast domain. So we're not talking about collisions when we're talking about broadcasts. More normally, when we talk about broadcasts, we're talking about an Ethernet frame where the destination address is all Fs, all hexadecimal Fs. In an Ethernet header, you have MAC addresses, and they're 48 bits long, or 6 bytes. So 6 bytes times 8 bits in a byte equals 48 bits. So it's a 12 hexadecimal string. The MAC address is 12 hex characters because a hex character is 4 bits. So it's 12 hex characters is twice as long as the byte count because a byte is 8, but a hex character is 4. All right, so when an Ethernet frame has a destination address of all Fs, that is a broadcast, and the extent to which that Ethernet frame can reach defines the confines of the broadcast domain. All right, so let's get back to the diagram. So now we have a broadcast domain. And when an Ethernet frame was sent from this computer to here, and the header had an all Fs MAC address, F, F, 12 hex characters of F in the destination address, this bridge would send it out, and it would arrive at all these devices. This is the extent of the broadcast domain. Now, if we connect this to a router, which is now a layer 3 device, now we no longer pass broadcast through the router. This is something that a router will not do. It will not pass a layer 2 broadcast in its typical form. In its default form, in its traditional form, a layer 3 device does not pass a layer 2 broadcast. It forms a broadcast boundary. Okay, you need to know that. We're not going to talk about all the things at the moment. We're not going to talk about all the things that you can do in more recent advances. Well, there were even some older technologies back in the day that would allow some bridging through a layer 3 device. And more recently in service provider networks or even enterprise networks with MPLS and layer 2 VPNs is what I'm alluding to. We're not going to talk about that at the moment. We need to get a good understanding of the traditional and basic functions of devices in the form of routers, switches, bridges, repeaters. We'll even talk about those in a moment. And layer 2 and layer 3 devices. Okay, so in their truest sense, in their traditional sense, this is what I'm describing. Okay, so let's get back to this. The router forms a broadcast boundary, and so if we have a similar network over here on this side, this forms, I'll just say BD, broadcast domain number 2. This is broadcast domain number 1 over here. Okay? So just like collisions do not go past the layer 2 interfaces of a bridge or switch. I'll start using the word switch because a bridge and a switch are very much alike. Just like a collision does not go past a layer 2 device, a broadcast does not go past a layer 3 device's interface. Okay? Okay, and I also want to mention that at layer 1 in the collision domain realm, just want to give you a little bit more history. The advances in technology a few decades ago got rid of the bus architecture of thin or thick net. And we got rid of the coaxial cable of RG58 for thin net or the other RG version for thick net. And these computers started being connected with a unshielded twisted pair cable, whereby which we could now in a data closet, in a closet we could rack mount a hub. I'm going to use the word hub, and we could run Cat5 or some type of Cat stands for category 5, 5E, 6. We could run a category of cable. It's unshielded twisted pair. It's no longer coax to each computer. Okay, so this was very nice. That I should mention that a break in the thin net of the old daisy chain methodology of these computers on a thin net, if there was a break in this cable, all these computers would be dead. They would go down. You had to have this thin net intact for these computers to work. If there was a break in the cable, this would be a bad thing for the LAN. Not so about the star topology, the hub spoke topology, or star topology as it might be called, of this newer technology that came about. And we're still talking the 1990s here, folks. Okay, so where you had the hub in the middle, you had computers radiating out from it. Here's the computers. And so if you had a cut in a cable, well, look, it only affected this one computer. It didn't affect these others. Now, early on, the hubs were also layer 1 devices. They would take in an electrical signal, a binary bit stream, and it would repeat it out all the other ports. It would rebuild the signal. So if there was a degradation in the signal, it would repeat it out at a new, increased, cleaned signal. But there was still CSMA CD technology existing in this device because it was a layer 1 device, and we needed to be aware that when this computer communicated, the other ones needed to back off and listen. So we still had the CSMA CD technology going on. All right? That was an advancement. When we got to where the new thing with switched Ethernet came about in the late 90s, I guess it was. We had switched Ethernet. We now had a very similar device, but now it was doing layer 2 intelligence, and the binary signal coming in would get reconstructed into an Ethernet frame. So this activity was basically taking at layer 1 and rebuilding this Ethernet signal up to layer 2 into the resulting Ethernet frame. So now this layer 2 device had layer 2 visibility, not just at the binary layer, but also at the bridging layer at layer 2. Okay, so now this Ethernet switch could make a determination of where it wanted to send this signal based on an intelligible Ethernet header. It could now look into the destination MAC address and decide where it needed to send this out. Okay, if it was a broadcast, it would send it out all these ports just like I drew. And just like in the layer 1 world, also in layer 2, it never sent it back. I'll just draw a big X here. It never sent it back out the port that it received it on. You need to know that. In layer 1 or layer 2, it would take the signal and send it to the other ports. In layer 2, if it was a broadcast, in layer 1, period, it would always send it out. I'll just put a check mark. It would always send it out all ports. That's just how it worked. But in layer 2, it only sends it out if it's a broadcast. But it does not send it back out the port that it receives it on. So you need to know that, okay? Now, something else that a layer 2 device can do. First, I'll mention that the whole idea, I'll just draw these ports like this, going to computers. The whole idea that this layer 2 device no longer propagates a signal to every port came to be known as micro-segmentation. You're micro-segmenting the network into these micro segments, okay? So now the collision domain became only between the interface on the switch and the interface on the computer. You had all these different collision domains now. One here, one here, one here, one here. And this is across the cable from the port on the switch to the computer down here. These are all computers. All right, that was the concept of microsegmentation. And so another thing that switched Ethernet at layer 2 brought to the table a nice capability was that to each computer, I'll just draw these computers like this, when an Ethernet frame is sent in, if it's not a broadcast and it's a unicast, that means that in the Ethernet header, the destination MAC address, if it, for instance, is the MAC address of this computer down here, the switch will eventually learn by building bridge tables, and I'll just draw entries in a bridge table like this. This resides in the switch, that by building a bridge table, it can efficiently forward this frame only out this port. The way that these bridge tables are built is on the fly, dynamically, as computers communicate, the source MAC address is snooped and listened by the port on the switch. So as a frame goes in this direction, the switch looks at the source MAC address, which would in fact be this burned in Ethernet address here, burned in address of that NIC, and it then adds an entry to its table, PC1's MAC resides on port 1, port 2, port 3, or port 4. It resides on port 1. Okay? So then that's at the beginning of time when this switch turns on, it doesn't have this table. This is a volatile table. It's built on the fly, and it's removed if this device ever reboots. Okay, so it's built on the fly. And at the beginning of time, this table does not know where this destination MAC is, which means the destination is unknown. So this is what we call an unknown unicast. It is not a broadcast, it's not a multicast, and we can talk about that later, but it is an unknown unicast. An unknown unicast is treated just like a broadcast, where as soon as this frame comes in, the switch will send it out to every port because it doesn't know where it is yet. However, it just learned where this computer is, so we build this one entry. When this computer receives it, it sends back a reply. The same snooping activity takes place, and computer number 4, MAC address for computer number 4, will be learned that it is on port 4. Okay, so you can see how this starts to get built. The reply, by the way, is efficiently unicasted back. Why? Because in step number 1, the switch learned the whereabouts. So now we have the efficient forwarding. Okay? This is how bridge tables are built, and some of the efficiencies related to Ethernet. Or I should say some of the efficiencies related to switched Ethernet. So it should start to become clear that a computer here talking to a computer here through an Ethernet switch, as that the computers are connected to the Ethernet switch with a cable, and as that traffic arrives at the Ethernet switch, that binary bit stream is reconstructed into an Ethernet frame, and now, that Ethernet frame is processed by the Ethernet switch using its bridge table with its entries. Bridging table, switching table, can be referred to as either. So we have layer 1, layer 2, the physical layer and the data link, data link layer. And so the switch makes a forwarding decision looking at the header at the destination MAC address. We already talked about how the table is built looking at the source MAC address, known as source MAC address snooping. It's a dynamic learning mechanism that bridges and switches comply with, and it's just an automatic mechanism. We already talked about that. So the Ethernet frame is forwarded based on its destination MAC address. If the destination MAC address is in fact the MAC on the NIC of this computer over here, then the Ethernet frame is forwarded across the backplane of this switch right here. It then descends the protocol stack, going back down, and is sent as an Ethernet, as a binary bit stream, arriving at the computer over here. And so we can start to visualize that as the signal is sent, it is processed at layer 1, then up to layer 2, across the backplane, back down to layer 1, across layer 1 up to layer 2, back across the backplane of the switch, down to layer 1, and across the cable. If we put a router in the middle of this, now we can imagine that we have the two layers as they pertain to a layer 2 switch, and as the traffic arrives at those interfaces. But we take it a step further with routers, whereas routers have 3 layers: layer 1, layer 2, and layer 3. The physical layer, the data link layer, and the network layer. Okay? And so the same is true, whereas the binary bit stream arrives here, we build an Ethernet frame, we make a determination using our bridging table entries in this switch's backplane, in its control plane, in its switch processor inside that switch. We make a determination, we forward the frame, send it back out as a bit stream. That bit stream arrives at the router. It ascends the protocol stack as an Ethernet frame. The destination MAC address is looked at. If it pertains to the interface on this router, then it's decapsulated, and now we have an IP packet up here at layer 3. We then, similarly, as we've talked about in with the switch, we similarly look in the header of the IP packet at the destination IP address. The router has a routing table. It is not built on the fly like switches build tables. The router builds routing tables based on protocols that are run with other routers, or based on subnets that are directly connected to it, or with static routes. We will get into more of that later. I think we'll cover some of that when we start talking about IPv4 and IPv6 addressing and subnetting and things like that. But let's just jump to the idea that here we have a layer 3 forwarding table, much like this switch had a layer 2 forwarding table. The layer 3 forwarding table in this picture is formed by the existence of 2 subnets connected to it. I'm going to draw a little circle here, this blue dot and this blue dot. So these 2 network interfaces have an IP address that exists at layer 3. I'll draw IP up here because it's a layer 3 thing. And so the IP address attached to the router here and attached to the router here will have to be 2 discretely different subnets representing this environment over here. Let me draw that differently. That subnet represents this environment over here, and this subnet represents this environment over here. Okay? And so this is a layer 3 subnet, subnet 1, or I'll call it subnet 2, subnet number 2. And this is layer 3 subnet, I'm scribbling. Subnet number 1. Okay? Subnets cannot cross interfaces on routers. You cannot have the same subnet on this router interface here as you do here. You will get an overlapping subnet error and you cannot configure it as such. With these two subnets directly connected to this router, you will now, in your routing table, in the routing information base, otherwise known as a routing table, you will have two subnets, subnet number 1 and subnet number 2. We're going to get into more specifics about what subnets look like. And so in this routing table, you'll have those two subnets. So as the traffic arrives at the router, the binary bit stream goes up as an Ethernet frame, decapsulated, then we have the IP packet. The IP packet header is looked at for the destination IP address. If it exists in this routing table, and it sees that the destination IP is in fact the destination IP of this computer over here, we'll say IP number 2. If we have IP number 2 in the table, and we'll talk about the specifics of what these routing tables look like later, but just want to get the concepts across. If it sees that in the routing table, and we'll call this port 0/0, and we'll call this one 0/1. If it sees it on 0/1, then that packet is then routed across the backplane. The packet then descends the protocol stack and is encapsulated inside of the Ethernet technology that exists on this interface. It's encapsulated into an Ethernet frame, goes down to layer 1, the bit stream goes across, and the switch does its thing. It looks at the Ethernet frame. If it's in the bridge table, it goes ahead and sends it across, and there we have it. So at this point, we can see that we've talked about collision domains as they exist between a PC and a switch, or a switch and a router. But we also talked about a higher layer broadcast domain as it extends from end to end on a router interface. Okay? We talked about how routers will not pass Ethernet broadcasts, but instead will route packets as intelligible IP PDUs, layer 3 PDUs. All right? Firewalls are normally deployed at boundaries of networks. We'll draw it like a brick wall here, and we will draw a router, a switch, and a computer. And this may go out to the internet, where really it's just a series of many different other networks all over the place that look much like this one. You know, that's what the internet is a lot of networks. Okay, and so you have yet another domain, so to speak. I would call this a security domain. This forms a protected enclave, so to speak. This is a protected environment over here. And this is the purpose of this firewall is to protect the internals of this network over here. This would be the unprotected side of this firewall. The job of this firewall is not to protect this side, but it is in fact to protect this side. This is an asset purchased by company A over here, or ISP A, back in here, inside here. It's owned and operated by that company, and it's for their purposes. And so traffic, as it exits the firewall from inside to outside, is not necessarily interrogated. It's trusted. This is the trusted side of this firewall. This is the untrusted side of this firewall. Okay? It is, in fact, the traffic that is initiated from outside going in, or from the unprotected side or the untrusted side arriving. Let me back this arrow up a little bit. As that traffic arrives at this interface right here, this is where the job of the firewall comes into play. This firewall, you can configure this to simply route it as if it was an IP packet and execute on what we have come to know about these protocol layers. Obviously, layer 1 exists. It always does, where the cable plugs in. Layer 2 is the Ethernet frame. Layer 3 is the IP packet. You could choose to route that right across layer 3 as an IP packet, or you could choose to, and that would be forwarding based on layer 3. You would really be diminishing the capabilities of this firewall to that of none other than just a layer 3 device, much like we learned about the layer 3 router in previous explanation. You wouldn't want to do that. You wouldn't want to go out and buy a firewall and allow it just to route. Now, you might do it on a selective basis. Maybe you trust this network over here with subnet number 3, IP subnet number 3. And so you might put a rule in place that allows that to simply pass through. But you don't trust the greater internet. You can't. There's billions of people in the world and millions of devices, and a lot of them are bad actors. And so that's the job of the firewall. It's to create a security domain. Now, before we get any further, I want to highlight the fact that the router does not see every Ethernet switch as if it was something that it needs to consider. If you have multiple computers hanging off of these Ethernet switches, then you have an Ethernet switch here connecting to another router, connecting to another Ethernet switch with a lot of PCs. We really need to understand that at a routing layer, this is a physical picture. I just drew a physical picture of what this network may look like. And at the routing layer, we really need to understand that at layer 3, if I drew this network up here at layer 3, it would look like this. In a layer 3 picture, I'll just draw that to terminate that segment. It would look like this. This is a subnet. We'll call it subnet A, subnet B, and subnet C. So this could be more like a layer 1 or a layer 2 diagram down here. But the router views the network like this. This would be more like a layer 3 topology diagram. This would be more like a layer 1 or a layer 2 topology diagram. Okay? And so this puts it in perspective as to how the devices view and forward or filter information. Similarly, if you're using firewalls, a firewall views the entire network of routers. If there's a few different routers off of here with switches and computers hanging off of them, and the internet, the firewall doesn't care about all these details. I'll put check marks. It doesn't care about all these details either. The firewall, if we're drawing a layer 4 security enclave or a security zone picture, as I mentioned previously, if I drew it down here at layer 4 and above, you'd have the picture of the firewall, and you have a protected enclave and an unprotected enclave, or a untrusted interface and a trusted interface. Okay, and so the job of this firewall is to protect this environment from traffic that will be coming in this direction. The intrusion prevention system, I'll draw it as a firewall. It's added capability to keep the untrusted side from wreaking havoc on the trusted side. The firewall does that, but the intrusion prevention system does it in a more intelligent way. There may be signature matching, there may be anomaly detection, there may be other things that it can do for traffic coming in this direction. So the intrusion prevention system takes it at a higher, it takes the capabilities up a notch. The firewall may be able to send rules to a router that might be connected to the internet, and it might tell the router to do certain things based on the IPS capabilities. And so I just wanted to mention that's gonna take it up a notch. Some of the capabilities of the router, if we have a couple routers here, we have the LAN segment with the PCs. The routers will typically forward the IP packet at layer 3 across its backplane and back out on the wire. You can take this up to layer 4. 1, 2, 3. You can take it up to layer 4 and do some controls based on the TCP or UDP port numbers. If you want to filter traffic in the router based on IP addresses or port numbers, this is known as a stateless packet filter or a stateless firewall, otherwise known as access control list, ACLs. Okay? Firewalls are more stateful type of devices where the firewall is aware of state tables of TCP or UDP. The firewall may also have something known as an ALG software capability in it, an application layer gateway, whereby which the layers that you go through here, you're going through layer 1 as the cable's connected to the interface, of course. Then you go to layer 2, layer 3, layer 4, but you might even go all the way up to the application layer, say for instance FTP or Session Initiation Protocol, a voice over IP signaling protocol. And so the ALG may be application aware of some of the dialogues and transactions that an application goes through, and you may be able to implement security based on application awareness. But again, at the router layer, you can dive deeper into the packet at layer 4 and implement a packet filter or an access control list on an interface as well. So there's some security and some added functionality. But I want to just be clear that the basic function of a router is what we've already discussed. It's routing packets based on their layer 3 information. Okay? The wireless access point is usually located on the LAN, where you have I'll draw it like this with antennas and a signal emanating out from it. and you have wireless devices that are within range with antennas, and the wireless access point will usually have a physical connection into the network, whether it's a switch, whether it's a router. And so we're providing Wi-Fi on the local area to the devices that are within reach. We use SSIDs for security on the Wi-Fi, passwords, various things like that. But this is what the access point is. There's a wireless access, a wireless LAN controller that exists in here to control this wireless environment. Okay. And what I'll also mention, Cisco Dna Center. We're not going to get into much detail about that, but Cisco Dna Center is a way of automating the provisioning of a lot of your networking devices. Okay, software defining and provisioning, monitoring, managing, a way of automating policy rollout for the way that you want to handle the traffic in your network. This is what Cisco's Dna Center does for you. And so we've covered a lot here. This was fun. It's always nice to talk about the intricacies of networks and how they function. And so I hope you're enjoying this. Please don't forget to like me if you like me, or if you like the video and the content. And so if you want to see more, subscribe so you can get updates. I've got a lot more to post. I'm looking forward to it. And also leave me comments if there's some things that you'd like to know more about or whatever. Then I'll circle back on it, or I'll state it in future videos. Okay? See you next time. Hey everybody, I'm back so soon. I needed to speak to something. When you're looking at a multi-port device, you can't, any kind of networking device, you can't tell if it's a old school layer 1 repeater, which a hub is another term for it. And you're not going to find one of those really these days. But you can't tell if it's a switch or a router or a firewall. You normally, I mean, you really just can't look at it and tell. You don't know what the capabilities of that device are just by looking at it. So gone are the days of some 24-port device being only a switch, okay? You need to look at the specs, the capabilities of that device to truly understand what it's capable of, okay? So I wanted to say that. Also, some devices are capable of multiple things, all right? So this is where the whole layer 2 switch, layer 2 device, layer 3 device, layer 4 and above device, does it bridge, does it route? There was even a term back in the day for a router. It was a bridge router. It could bridge and route. Well, you know, or a MLS, a multi-layer switch. And so really it's all about what we've been learning. Can the device forward traffic at layer 2 from one port to another? Can it forward it or segment the layer 2 domains into broadcast domains and put IP addresses either on physical ports or in logical ports? We can talk more about logical ports later. But can it do that in such a way that it forms layer 3 separation, thus separating broadcast domains and having discrete subnets on those separate broadcast domains? Can it do that? Furthermore, how scalable is it in its form in its ability to do that? Meaning, does it run routing protocols? Is it designed to be a router, or is it just a low-cost router and it doesn't really run routing protocols? I mean, the router in your home on your broadband internet connection is in fact a switch with its multiple physical ports as well as the antenna going to the Wi-Fi of your house. It's performing layer 2 forwarding between the physical ports on those LAN ports and the wireless environment. It's bridging. However, in software inside the device, there's a layer 3 interface that routes into a small firewall capability in your router in your home. We're talking about residential grade devices that bridge or otherwise in a switch, that route and that perform layer 4 and above firewalling functions. And another thing that it does is network address translation, where it translates public and private IP addresses, and we can talk about that a little bit down the road as well. But I wanted to talk about that in conclusion to this network devices, roles, and functions. That's on a small scale, the one I just described. In a business grade or a service provider class router, you could have a router that's, this big or 6 feet tall. No kidding. With modules and slots. Could be a multi-million-dollar device, and you could have a slot in this modular router in a data center or an ISP communication building in your neighborhood or in your city somewhere. One of these modules could be a firewall module. You could have other modules for routing and switching capability. And so this device could be multi-layer capable. Now, all that to just conclude this, because you really need to just be comfortable and understand at a basic level what happens at layer 1, what happens at layer 2, what happens at layer 3, what happens at layer 4, and above, okay? Once you get comfortable with that, you can take that knowledge and apply it to the smallest or the largest of the devices, because you've now become aware of the processes and procedures that happen at these multiple levels of the communications model. All right? I hope you're getting a clear picture of what goes on in networks and devices and things like that. I look forward to the next video. Thank you.